for a rotation about an axis pointing in direction n, a small angle delta theta rotation gives rise to change delta r is equal to delta theta cross r. If I divide by delta t, I get the velocity is equal to this, I write as the angular velocity omega cross r. This is being very, very specific to the vector displacement vector r. In general, rate of change of a vector rotating about an axis pointing in direction n is going to be equal to omega cross a. Another general result. These are very, very useful result for use in rigid body dynamics, and we will be making use of them quite frequently. Just like delta theta can be represented as a vector, delta theta over delta t can also be represented as a vector, which I now call angular velocity. So, second thing is angular velocity, which is delta theta over delta t, a vector. The answer is yes. Omega is a vector quantity with direction along the axis of rotation, and the sense is again right hand rule. If something is rotating like this, the thumb gives me the direction of omega. You may ask, so what? I have identified omega as a vector quantity. How does that help me? See, in physics, when I take a quantity, it has to be either a scalar or a vector, then I know exactly what kind of algebra I can perform on this. So, identifying the angular velocity as a vector quantity does give me a handle on things. For example, let me just illustrate this with a very simple example. If I take a ball, a solid ball, give it a spin omega about an axis and leave it on the floor, which has friction, at an angle theta from the vertical. The axis of rotation makes an angle theta with the vertical. And now I ask, what would be the eventual rolling speed of this ball? I know if omega points exactly up, then the ball cannot roll. Eventually it will stop. I know if it is pointing this way, it will roll with certain speed that we can calculate. How about when it makes an angle? Now I make use of the vector nature of angular velocity, take its component in this direction omega sine theta, and take its component in this direction omega cosine of theta. And these are two independent vector quantities, omega sine theta, omega cosine theta. Omega cosine theta cannot contribute to rolling at all. So, eventually due to friction it will stop rolling, it will stop rotating like this. On the other hand, omega sine theta is responsible for rolling. So, the question I may ask now, what if I take a ball and rotate it with a speed omega sine theta and leave it on the floor with the axis of rotation horizontal? What will be its rolling speed? You can calculate that using the techniques that we use in the first 3 lectures. Its final speed comes out to be omega equals 2/7 omega r sine theta if r is the radius of the ball. So, you see, we could do this right away because we identified omega as a vector quantity and could take its component and realize that only the horizontal component contributes to rolling. Now that we have identified the angular velocity omega as a vector quantity, the next question I ask is, if to a rotating body I apply an external torque tau, how does omega change? with time. The equation I know is that dl over dt is equal to tau external. So, to relate the change of omega with tau external, I need to relate L and omega, the angular momentum and omega, and this is what we do next. We have already done it in simple cases where we wrote about when a body was rotating about a fixed axis that L was I omega, but now we do it in general. Suppose we take a body which is fixed at one point and it is rotating with some angular velocity omega, so that if I take x, y and z axis, there is a omega x, there is a component of omega in this direction omega y, and there is a component of omega in direction omega z. What is this angular momentum about this point? So, right now what we are taking is a fixed point rotation. I know if the body is also translating, we can always go to the center of mass and calculate the angular momentum of center of mass and angular momentum about the center of mass, and we can do a motion, a general motion also. So, as long as I can do a fixed point rotation about the center of mass or any other point, the general motion is no problem.